All right, let's get started. Hello, everybody. Welcome back. So I noticed most of you submitted already the first homework, which is good. Just to clarify, the submission really is completely electronic. I don't need to, no papers or anything. Whatever files you feel like you want to submit, you can just zip together. This time, just the M file should be fine. So I think most of you got it right. So that's good. I also just released, or maybe a little bit earlier, I released a new homework, which will be on this topic, practice with coordinate transformation. So all that we'll be talking about today, you will actually get to do, to play with for real. So there will be like a little bit of applications already. Somebody was asking me last time, like this is still like basically full-fledged linear algebra course. It's not like we wouldn't really do the theory. I don't know how we could do the applications of the theory without going over the theory in the first place. The difference to the linear algebra course in the math department is that we are not so after all the proofs and so on. It's more about the intuition and the applications in this case. I think I discussed it before. I just want to clarify. Some people are asking about that. All right. So let me start, because the topic of coordinate transformations basically builds up on what we were talking about before on linear transformations. Let's do just a very quick review of linear transformations. That's what we were discussing the last lecture, if you remember. If you don't remember, I will very quickly review it. So a transformation between two vector spaces will be called linear if and only if what is true. This is, by the way, one of the things you should really remember, the definition of a linear transformation. We will need it at one point in this lecture exactly to prove that linear transformation keeps zero vector at zero. So this, you don't have to remember a lot of things in like mathy type of lectures like this one, but a few things like the definitions of the basic properties you do have to remember also for your midterm exams and finals. So the linearity requires that for any scalar alpha, any vector v, and any scalar beta, and any vector w, this is true, right? This is not true, but this is true, plus beta t w, right? I already discussed it quite a lot before, so I'm just reminding you this. In our case, this v1 is typically some R2n's linear vector space, and this v2 is R2m in general, right? There's nothing, of course, preventing us from having n equal to m. That's perfectly fine. In fact, in that case, lots of things simplify. And let me try to be more interactive. Actually, if you still have the name tags, maybe if you don't mind putting them up, I will still try to look at you and remember you a little bit better. So my first question is, just if you remember from the previous classes, if you have a linear transformation like this, going from R to n to R to m, it's representing using a matrix, right, with respect to chosen bases in these two spaces. So by default, we choose the standard bases. And what dimension matrix would this be, representing this linear transformation? Basically have two options. two attempts. So let me repeat the question in case you were busy preparing your name tags. So we have this linear transformation operating, mapping vectors from R to n to vectors of R to m, right? That's the deal. This is the input to the function. This is the output of the function. We know that the function is linear from what we talked about with respect to standard bases in both R to n and R to m. And I hope you remember how standard bases look like. With respect to the standard basis, we can represent it using a matrix, right? So the matrix, I will call it A. And I want you to tell me what dimensions should I write here. So this n is the dimension of the input space, m is the dimension of the output space, right? So that ultimately, when I have the matrix, I can represent this transformation as a matrix vector multiplication. That's exactly what we discussed the last lecture. Okay? So just somebody give a guess. N by m. Let's see. So let's do n by m. So that's exactly. It could be n by m, or it could be m by n, right? Which one do you think is right? Here it sort of suggests n by m. Well, the key is to remember, if you want to get this right, as opposed to just guessing, the key to remember is, you know that the action of this linear transformation will be writable as matrix vector product, right? AX, right? So that, remember, so if A is an n by m matrix, what dimension must be the vector x? So A times x is defined. So let's assume that A is n by m. And if I'm doing A times x, what does it mean about x? X certainly cannot be arbitrary, right? It must be dimension, what? M, correct. Oh, I don't have your name there, man. So that would not work, right? Because the x's, they come from the V1 space, which is R to n. So the x's will be n-dimensional, right? So actually, this is not the case. So the matrix will be m by n. And if you find it confusing that the mapping is from R to n to R to m and the matrix is m times n, you are not alone. I also find it weird. I don't know why the convention was chosen like it was chosen, but that's what it is. It was not my idea. So indeed, the matrix means mapping from n-dimensional space to m-dimensional space. And that's because of how matrix vector multiplication was defined. How was it defined, by the way? Let's recall that too. So if I have established that my matrix is m by n, that means that the x vector must be n-dimensional, right? And by I mean the ith element of this n-dimensional vector. So here I goes from 1 to n, okay? So how was this defined? Anybody remembers this? This is also one of the things you actually should remember. You don't have to remember the formula, sort of like memorizing the formula, but you need to remember some sort of recipe how to reconstruct the formula. If someone corners you at a door and wants the formula, you should be able to figure it out. You don't have to have it like right in your memory, but you might have like this picture of like taking the matrix, taking the vector, taking the dot products. From this picture, using your intelligence, you can get the formula. But you need to have the first piece of information there. So okay, I won't be torturing you any further. I will just write it down. So I'm summing over columns. That means I'm going to m, and it will be going over the ith row, going over all columns, and multiplying with the elements of x. And it goes from, for i's, from 1 to n. Did I do it right? I always need to check. I think I did it. Wait a second. M is the number of rows, n is the number of axis, and then, oh, wait a second, here is the mistake. The I doesn't go, yeah, always have to be careful. There's only one, there's always just two possibilities. I need to be careful what one is right. I think that the I needs to go to m, because AX is an m-dimensional vector, right? So this should have actually been n. Because again, so actually it's probably better to draw the picture, right? So because I'm also very easily confusing myself. So this is m is, so remember, m is always the number of rows. The first index here, or the first number here, the first symbol here is the number of rows. The second is always the number of columns. If you get confused just by drawing these pictures of the matrices, and by the picture of the matrix I mean this, right? A11, A1n. Sorry, not my best n. This is AM1 up to AMN, right? And hitting it with a n-dimensional vector means doing this. This would be vector x. So indeed, the result is indexed from 1 to m, and the sum goes over j from 1 to n, okay? So this is how you can reconstruct this formula if you need to code it upward or something. Make sense? Good. And the last very important thing or I guess if you just want to remember a few things from the last lecture, the one more thing I would like you to remember is the rule for composition of transformations, which corresponds to matrix multiplication. So let me write it down, because I think it's composition transforms corresponds to matrix multiplication. And we discussed this at length the last time. Let me just remind you the formula for matrix-matrix multiplication, because that's something we will be using from now on all the time in the course. Okay. So if I have two matrices A, so A would be, let me write it like this. A would be an M by N matrix, and B would be an N by K matrix. So this N I did not choose arbitrarily. This dimensions have to match so that the product AB, which would be some matrix C, is defined, and that would be an what dimension matrix? If it's a product of A and B, which are M times N and N times K, what's the dimension of C, which I write there?
M by K.
M by K, that's exactly right. Yes, thank you. And how do I compute the elements of this matrix? So the element on row I and column J of matrix C, that's how I denote it. C is my M by K matrix. That's extracting one particular element out of it, right? And what's the value for it element? Again, I don't expect you to memorize the formula, but you should be able to produce it just from your memory. So the main problem is always to get the indices right. So the formula looks like this. Oh, see, and I again got it wrong, just to show you how easy is it to get it wrong. So this is IL times BLJ. Okay. So the thing you can remember is you sum over this shared middle index, if you will, which exactly corresponds to the fact that this N needs to match this N. Okay? So this was matrix multiplication in a nutshell. The key is that if the matrix is A and B, and the matrices always represent sublinear transformations, so if you imagine the matrices are representing some linear transformations, then the matrix multiplication represents the composition of these transformations. Okay? All right, so let's start by studying particularly important case of linear transformation. So that's the new stuff, or maybe you have seen this before. Super important example of linear transformations are rotations. So let's go through it one by one. We will start by rotations in the plane, and that's what we need to eventually build up to coordinate transformations. So, okay, so what is a rotation in the plane? Well, rotation in the plane is something very simple, right? It is an operation that takes a vector and returns a vector which corresponds to rotating that vector about an angle theta about the origin. Okay, so your picture would be like this. So I have some vector with coordinates x and y. And what the rotation does, given an angle theta, so if it was something like 30 degrees, it would do something like this. So this would be the input vector. This would be the output vector. Okay? Now it's possible to show that this is a linear transformation. This will be sort of obvious from what we do next. So all we need to do is, again, that's one general thing we had last time, right? That the linear transformation is completely characterized by its action on the standard basis vectors. Okay? That's really what led to the matrix, right? Because this matrix of a linear transformation, the columns of this matrix are nothing but the action of the linear transformation on standard basis vectors. Again, reminding you one more thing from last time. Okay? So the same thing goes for rotation. So the standard basis in R2 is really simple. Those are these two vectors, right? Sometimes I was denoting them as E1 and E2, but they are just this in 2D, so it's quite simple. So how do we find the action? We need to numerically compute what is the rotation of these two vectors. So let's first take a look at the first one, the E1, which looks like this, right? If this is my x-axis, this is my y-axis. Let's say this is 1. So this would be my E1 vector, right? Represented by this arrow, right? And I need to compute, I need to figure out what the vector will be after I rotate this E1 by angle theta. By the way, by convention, if I say rotate, pretty much universal in mathematics, it means rotate counterclockwise. Okay, that's the standard convention. If the angle theta is positive, if I like want to rotate it by 30 degrees, that means counterclockwise. Again, very standard convention. So, any ideas? How do we compute it? So let me start by amusing you by trying to draw a circle. That's always, because I never get a very good circle, but I hope something like a circle. Imagine that's a circle, okay? So if I'm giving the angle theta of the rotation, right? So let's imagine something like this. This is my theta, right? And what I need to compute is this x and y. That's basically the result of rotating this vector 1, 0, E1 by angle theta, right? So does this ring a bell? Does this ring some basic trigonometry bell, which is cosine and sine functions? Yep.
So the x component would be the radius times the cosine of theta.
So the radius is 1, right? That's why I sort of conveniently said it's 1. Yeah. So
Cosine of theta.
cosine of theta and sine of theta. Yes, exactly. So you know from a triangle, if this is 1, that's because I said this is a unit circle, even though it looks more like a potato, but it's a unit circle. So this is the cosine of theta, this is the sine of theta, right? So that means rotation of this vector is this. So if I want to represent the rotation by a matrix, I already know what's the first column of the matrix, right? So first of all, it's going to be 2 by 2 matrix. Rotation is a linear transformation going from R2 to R2, right? That's so obvious. I don't think I need to write it. And the first column will be cosine theta, sine theta. That's because the rotated x is cosine of theta, rotated y is sine of theta. Everybody got it? So that's the first column of my matrix. How do I get the second column? So the second column, well, what is the second column? Well, that's the rotation of my vector 0, 1 by angle theta in the plane, okay? So similar picture, right, like before. So this is my picture. I hope it's not making you dizzy by switching this line. Now we are rotating which vector? This vector, right? So if this is 1 here, this is my vector 1, 0, aka E2, the second standard basis vector in the plane, right? And I'm again rotating it some theta degrees or radians, whatever you want to measure angle in, right? So this will be again unit thing, and I want to get the x and y. And again, I need a formula for x and y depending on the angle theta. So any ideas how to do that? There are actually, I know at least 2 ways how to do that. They're both fairly simple. So either your trigonometry foo is strong with you, and you know, so you can basically realize, okay, so this is 90 degrees, right? So this is basically rotating this E2 by theta degrees is the same as rotating this E1 by 90 plus theta degrees, right? Or pi half if you are computing in radians like MATLAB plus theta. And if you remember the trigonometry formulas, there are formulas which say that cosine of theta plus 90 is what? It's minus sine of theta. Let's not forget the minus sine of theta. And sine of theta plus 90 degrees, I guess, is what? It's cosine of theta. And that's indeed exactly the second column, minus sine theta, cosine theta. And again, it's the rotation of the E2 vector by angle theta in the plane. Again, counterclockwise, of course. It would be clockwise if the theta was negative. Okay, if I said minus 30, that would mean rotate clockwise, all right? But the other way you can see this is that basically if you rotate it this entire frame, then this second vector needs to stay orthogonal to the first. So if I like rotate this entire thing, so this vector, I guess, let's call it E1, E2, this would be like rotated E1, rotated E2. You can sort of see that the rotated E2 needs to stay orthogonal to it. It's actually a property we will prove formally later. So you could just say that I need to find a vector which is orthogonal to cosine theta and sine theta. And in general, if I have, by the way, that's something generally useful. If I have a vector x and y in plane, how do I get a vector orthogonal to it? Slightly tricky, right? Because you can think about at least two of them and their linear combinations, but if you want to just sort of rotate counterclockwise by 90 degrees a vector x, y in plane, what would you immediately write there? So if I want to rotate by 90 degrees counterclockwise. So who wants to say it? There's some, yeah. Huh? That's right, yeah. So you can do minus y. It's very obvious if you draw the picture, right? If I have again, these arrows can get you long ways, right? So if this is x and this is y, so let's try. So minus y becomes x, right? So that means this is my new x, and x becomes y, right? So I get this vector, and that looks like right, huh? That looks like 90 degrees rotation. I could also write y and minus x. That would also be correct, except that would be the other way around. That would be the clockwise rotation. Okay. And indeed, if I do this counterclockwise 90 degrees rotation to x and y, and my x and y is cosine theta and sine theta, I again get the same thing. All right. So that was just two different ways to convince you that this is the matrix representation of a rotation by angle theta, counterclockwise rotation by angle theta in the 2D plane. Rotation matrices are really important. They have a number of very useful properties. So let's start with the most simple one. By the way, rotation matrices in higher dimensional spaces, in 2D it's all very simple, easy. I can just draw this vector, the arrows in the plane. And in higher dimensional linear spaces, that will be a big part of what we'll be talking later about single value decomposition, eigendecomposition. Rotations play a major role there. Higher dimensional, multi-dimensional rotations. And we get there by sort of studying the rotations in the low dimensional spaces, and then we sort of generalize the properties that will give us an idea how to define rotations in higher dimensional spaces. Just like a justification or motivation for what we are doing. So let's see some of the most obvious properties. One of them we actually sort of already noticed. So the first thing you can notice is that the columns are orthogonal. Everybody sees that? So because the columns I can view as individual vectors, right? I guess that's what's written here. So if my ux is cosine theta, sine theta, uy is minus sine theta, cosine, so that's the first column, second column. If I do the dot product, now we have to remember how dot product, I hope everybody remembers how dot product is defined. So the dot product will be cosine theta minus sine theta plus sine theta cosine theta, which is obviously 0, right? Because this is minus the first thing. And we know that dot product equals 0 means that the two vectors are orthogonal. All right? The other interesting thing is that each of the column vectors, both ux and uy, they are actually unit vectors. Why is that? That follows from the basic trigonometric identity that cosine theta squared plus sine theta squared is 1. It's exactly what we have in both of these vectors. Here is this little minus, right? But that doesn't matter because if I square it, the minus goes away. I'll just get sine squared plus cosine squared. That's still 1. Yep. So the matrices with these properties are called orthonormal matrices. That means orthonormal means orthogonal plus having columns of unit length. That's exactly what rotations are, orthonormal matrices, or the matrices representing, I guess if you wanted to be like really careful, with the lawyers present, you would say that matrices, or you would say that rotations are the linear transformations, and the matrices that represent linear transformations, the matrices that represent rotations are orthonormal matrices. Just sort of distinguish between the concept of transformations and matrices, okay? Here is one more property of rotation matrices. I sort of intuitively said it before, so maybe it makes sense to try to prove it, to put it on more solid footing here, actually trying to compute it. So the good thing about rotation matrices is that they preserve both length of vectors and the angles between vectors. So what do I mean by that? If I give you a pair of vectors, some vector, I don't know, x and y, and I rotate the entire thing, I guess I could do it like, let's try it like this. So let me do again. So this would be one vector x, one vector y. They both go from 0. And you know how to compute the angle between them, right? Using the dot product. You must know that. The thing is that if I rotate this entire thing, if I apply some rotation matrix and compute the angle again, I must get the same angle. So that means rotations preserve angles, okay? And because both angles and lengths are are basically just different aspects of the inner product, it suffices to show that rotation matrices preserve inner product or dot product. So let's take a look at it. That's the proof is right here. It's fairly simple. So if my first vector has coordinates AB and CD, so let's imagine this guy has coordinates AB and this guy has coordinates CD. They are both 2D. So this is again just writing out the matrix vector product. I guess I could have said it on this slide already. So if my matrix R theta has column vectors ux hat, uy hat, the hat's because it's a unit vector, then R theta times xy is x times the first column plus y times the second column, all right? And I am using it here in this proof because R theta times AB will be A times the first vector plus B times the second vector, ux hat, uy hat. This is the same rotation applied to a different vector. So the ux hat, uy hat is the same, but there are different coordinates of the vector, this time C and D, okay? This thing in between them is the dot product, all right? So now we can apply distributivity, right? Because this is a dot product between sums of vectors. So we had, I think was the first and maybe second lecture where we talked about the distributivity of the inner product. So that's what we apply here. So it distributes to this long sum, or not that long, but 4-term sum, where we have the individual dot products, okay? And what happens here? We know that ux and uy are orthogonal, so this dot product is 0. So that goes away. This is 0. Same thing here, uy, ux, again, you know that dot product is commutative, also 0, goes away. And ux, we said that is a unit vector, so this is 1. Same thing, uy dot uy is 1. Okay, everybody follows? So this reduces to AC plus BD, which is nothing but the dot product of AB and CD. All right. So let's take a step back and think, what does it mean? It means that it doesn't matter if I rotate the vectors by a rotation of theta, both rotate by the same rotation, and then take the dot product, or if I just take the dot product of the unrotated vectors. So just the picture I was sort of trying to animate before, that the dot product doesn't change with rotation. I can be rotating this all I want. The dot product between the vectors will always be the same. That's what's summarized here. For any two vectors, they could even be 0 or whatever odd case is, right? Or negative, whatever. The rotation does not change the dot product, the inner product. Of course, if it doesn't change the inner product, it means that it doesn't change the length either, right? Because how is all the length the norm? Because how is norm defined? Norm is just the inner product applied to itself, right? So let's take a look at the length of vector u after rotating it by angle theta. So, and let's make it square. The squared length of vector u after rotating it by angle theta by applying the matrix A theta. Well, it's nothing but r theta u dot product r theta u, right? So that's just a special case of this formula we have just derived, which means that this is just u dot u, which is by definition the square norm of u, right? I can easily take square root on both sides, and I can see that indeed the norm of the rotated vector is the same as the norm of the unrotated vector for any vector. Everybody copies? Good. That's sort of obvious, right? That by just by rotating vectors, I should not be able to change their length. All right, so rotations are like a basic example of a linear transformation and like a basic basic ingredient in coordinate transformation. That's what I'm trying to get to. Now, even more basic operation than rotations is translations, right? If I just want to translate things. So let's talk about translations a little bit. There is an interesting catch. If you know something about graphics, you have already seen it because that's a common thing there. So translation means basically I have something and I just want to move it, just want to translate it. It's even a simpler thing than rotation, right? So describing translation mathematically is super simple, right? In our vector formalism. All that means is just add a constant vector. Okay, if I wanted to write it by coordinates, I have Vx and Vy, and I just add Tx and Ty. That's what this means, written by coordinates. Nothing special is going on here, right? Why do I even bother with this? Where here T is the translation vector, right? Translation vector is sort of the analog of the angle of rotation. That's sort of the parameter of the transformation. Oh, speaking of the parameter of the transformation, this is something about rotations I forgot to mention because I'm sort of trying to rush to cover all of this, but let me mention this because it's important. I said that rotations are linear transformations, right? Which is certainly true. I can represent them by a matrix, so that's good enough for linear transformation. But certainly cosine and sine are not linear functions of theta, right? So if you have, whenever you have fixed theta, and when we have given a rotation, that means a given angle of rotation in 2D. In 3D it will be a little more complicated, but the idea is the same. For given rotation is a linear transformation, okay? But if we are talking about families of rotations, when we are varying this angle theta, it's no longer linear, right? There is no way in hell that sinus x plus y could be sinus x plus sinus y, right? That's absolutely not true. And that's what would have to be true if it was to be linear with respect to theta, right? So this linearity refers to linearity with respect to x and y, with respect to the input parameters of the rotation, not with respect to the theta. Got it? That's also why like algorithms like inverse kinematics and so on, when you are solving, that's used in robotics, when you are solving for the thetas, that results in nonlinear algorithms. Because once the theta becomes unknown, you go immediately to nonlinear problems. Exactly because of these sines and cosines, which of course are nonlinear functions. Now here is another interesting thing. Here it's actually easier. The translation, believe it or not, that's also not a linear transformation. Have you seen that before? Have you had some graphics or something? Some of you did, some of you probably didn't. So I'll explain that because that's definitely worth explanation. So I guess this is one reason why translation. So translation is an operation. It's also, so translation T, it's also operation going from R2 to R2, right? What does it do? I guess if I was to illustrate it graphically, if my translation was like this, that would be my T. And if my input vector was, for example, this would be my V. And I would just basically do this, sum it together, and this is my result, right? V plus T. So basically, if I had a point living here, the point gets translated over here, right? The problem is that transformation is also not a linear transformation. In this case, okay, I need to be a little bit careful. In this case, the translation itself is not a linear transformation. Rotation is a linear transformation if I don't fiddle with the theta. But translation, even if the T is kept fixed, is not a linear transformation, okay? And it's quite obvious. It goes directly from the definition, right? That's what I started with. That's what I was saying, that you need to remember the definition of a linear transformation, right? Definition of a linear transformation requires that the transformation T of alpha V plus beta W is alpha TV plus beta TW, right? Unfortunately, for translation, that's not true, because if I translate alpha V plus beta W, what I get? Well, I get alpha V plus beta W, right? That's the V that just gets copied over there, plus T, right? On the other hand, if I first translate just V and multiply it by alpha, so translating V means V plus T multiplied by alpha, that's this alpha here, and translate W, so I guess I could write it down like, so this V plus T is my TV, right? W plus T is my TW, so here you can immediately read this right-hand side of the defining property of linear transformations. And as you can see, this is alpha V plus alpha T plus beta W plus beta T. Well, there's a problem, right? There is T on the left and alpha T plus beta T on the right. And that would have to be true for any alpha and beta. Well, that's not possible, right? It'd only be true if alpha and beta happen to be 1, but that doesn't matter. It would have to be true for any alpha and beta, so that's clearly not the case. Everybody got it? Here's another reason why translation cannot be a linear transformation. All linear transformations have to keep 0 at 0. So, now it's confusing. Now T is, so let's say that L is a linear transformation. And what I'm saying is that L of 0 must always be 0. You can like say it's like a little lemma or something, or a fact. Why that is true, you can prove it. I don't think the proof is terribly useful, but here it's sort of how it's done. So I can certainly write 0 as a 0 scalar times 0 vector, right? Because L is linear, I can write it, I can take the 0 out. That's again the defining property of linear transformations. L of 0, scalar product. But I know that 0, scalar product of 0 times anything, scalar product of any vector with 0 is a 0 vector, right? So I have to conclude that linear transformation of 0 vectors is 0 vector. This is an example where I think proof doesn't really give you much of an intuition why this is true. Did it give you much of an intuition, this proof, why a linear transformation have to keep 0 at 0? Sometimes people say it's like the fixed point of the transformation. It can be even rotation, right? Think about rotation, that's what we had before. Rotation takes a vector, rotates it around. Applied to 0 vector, it absolutely has to keep it on the spot, right? I don't know if this proof gave you much of an intuition why linear transformation has to keep 0 on the spot. It certainly didn't help very much to me. Here is another way. This is, by the way, why I sort of prefer this not 100% mathematically rigorously correct introduction to linear algebra, because I think it's much more important to understand why is it true than being able to formally prove that it is true. Here is an intuitive way to understand why zeros must be mapped to zeros by linear transformation. 0 vectors must be mapped to 0 vectors. Well, we know that linear transformations can be represented by a matrix, right? Doesn't have to be square, it can be rectangular. So if I apply the matrix to a vector which has all zeros, well, then it's very obvious that no matter what is in the matrix, there can be crazy numbers, they can be zeros, they could even be complex numbers, I don't care. The result will always be 0. Right? There's absolutely no way how linear transformation could map a 0 vector to non-zero vector. Unfortunately, that's exactly what translation has to do, right? If I give v0, it has to map it to t. The translation has to translate everything, including the 0, right? It can't be a linear transformation, we just do the 0 phase, okay? So that's why we move to affine transformations. So we sort of we have to do something about it because linear transformations couldn't model translations. So we say instead the translation is an affine function. And here is a formal definition of what is an affine function. Affine function is a function if after I subtract the transformation of the 0, I get a linear function. So this is basically like a funny mathy way of saying that affine transformation is translation by a constant t vector plus linear transformation. Like, I can sort of say it like this. Affine basically is linear plus translation. All right? Basically what happened, I realized that translations cannot be represented as, translations are not linear transformations. So what I do, I invent affine transformation simply by adding translation into the picture, right? So I guess if I was to do a 2D example, like fxy being 2x plus 5y, that would be an example of a linear transformation. If I put there plus 7, that would be an example of an affine transformation from R2 to R1. Make sense? I'm not quite sure what you are writing down. This is sometimes called the affine part of the transformation, like that. That's the constant translation. Okay, so we are finally trying to get to coordinate transformations, which will be affine transformations, because they are very important, not just in graphics, but also in vision, robotics, mechanics. There is an example how it matters in robotics, because if you have a robot, what is a robot, really? Robot is basically like some mechanical structure which combines lots of rigid pieces together, right? If you take the skeleton of the human, that's also something sort of like a robot, right? Because you can look at it as bones, which are basically rigid bodies, which are connected using some joints. So basically a robot is sort of trying to do something like a human body, but engineering as opposed to not. And the rigid bodies, they are connected by some joints. There are different types of joints. You can rotational joints, translational or prismatic joints. Sometimes, quite often on the robot, you have some cameras mounted, right? Because the robot usually needs to see the environment it's in. And one of the basic things in robotics you have to wrap your head around is how all these coordinate systems, how the transformations between the individual rigid bodies relate to each other. Because each of the rigid bodies typically has its own coordinate system attached to it. Basically, what I mean by coordinate system, coordinate frame of reference, is something which with respect to what I can measure coordinates. Okay. So for example, the camera there, it's mounted on one of the rigid pieces, right? The camera itself is a rigid piece. And it measures the world, it measures what the robot is seeing in its own local coordinate space. Okay? But when the robot needs to do something, needs to like move or move the arm, I might need to convert the coordinates from the camera space to the coordinates of the hand, because in the hand there might be some mechanism which can actually do something, right? So converting between coordinate transformations, that's basically the cornerstone of robotics. That's the basic building block of robotics. And consequently, like human animation, for example, in computer graphics, character animation. So we distinguish two main types of rigid transformations. The ones that, we distinguish two main types of affine transformations. The ones that are rigid and the ones that are not. So rigid transformations are transformations which correspond to motion of a rigid body, right? If I have a rigid body, both in 2D and 3D, what it can do, it can translate, like a rigid body like this pen. It can translate and it can rotate, right? It turns out that the most general form of a rigid transformation is a translation plus rotation, okay? Linear transformations can do more. Linear transformations can also do scaling and shearing or even a reflection. That's something that rigid bodies certainly cannot do, right? Like the simplest example of scaling is something like this. If I do a non-uniform scaling in the x-axis, I get something like this, right? It's not a rigid transformation. Elastic deformable object might be able to do that, might be able to do non-rigid transformation, but certainly not rigid body. Rigid bodies are most important because in robotics, that's how we model the individual pieces of the robot. Even though, bear in mind that in nature, rigid bodies don't really exist, right? Everything, even bones and all these, are to some small extent deformable, but to the extent of the approximations we are making here, the rigid body is a very good approximation of that. Yeah, and here is the cool thing. Any rigid transformation really is just a combination of translation and rotation. Well, debating whether I will elaborate on this more. You know, let me first cover this, and then I can elaborate on the things I consider cool. Just be a little bit disciplined. Okay, so let's talk about coordinate transformations, because this is what you will need for your project number 1. I guess the assignment now is called a project instead of a homework. Don't be confused. I guess that just means there's a little more programming. By programming, I mean MATLAB programming. So let's first talk about how do we measure coordinates in coordinate frames. So what is a coordinate frame is basically just a point in space. If I was to be formal, I would say a fine space, but I think the intuitive understanding here is sufficient. So if I have one coordinate frame called A, which has some origin here and has two set of basis vectors. In 2D it would be just 2. You could say that this is like the x vector of the coordinate frame. This would be the y vector. So if I am given a point P, it has some coordinates with respect to the coordinate frame A. Okay, how do I get it? Well, what do I do is I just take the vector PA, which subtracts the vector P from the origin of the coordinate frame, and then I do orthogonal projection on the basis vector. So if I extend this guy here, this would be my first coordinate, my, I guess, how is it called? PAX coordinate or something, or I guess XA. Same thing for the y-axis, right? This would be YA. So the XA and the YA are my coordinates of point P with respect to the coordinate frame, or just frame A. Okay? And the motivation is what I was saying before, like if you have a robot and you want to convert from coordinate frames associated with different lengths of the robot, that's what we need here. So if I have a different coordinate frame, For example, imagine this would be the coordinate frame of the camera mounted on the head, and the B would be the coordinate frame of some sort of manipulator mounted at the arm of the robot. So I want to compute the coordinates of the same point with respect to this different frame of reference, with respect to different coordinate frame. How do I do it? Well, the same way, right? I subtract the point P from the origin. This would be my origin of the coordinate frame B. And I do orthogonal projection on the axis. So this would be my XB. And this here would be my YB. So here by YB, I mean this distance, right? This length here. And the XB would be this length here. All right? And what I want to know now, I would like to represent, I would like to wrap my head around the transformation of coordinates, right? Because the point P, I can measure with respect to many different coordinate frames. Here is the frame A and frame B. And the question I have is, how do I relate the PA, the vector of XA and YA, to the vector of PB, which has coordinates XB and YB? How can I elegantly, easily convert coordinates between individual coordinate frames? Lots of applications you will be doing in project one. You will be displaying like a moving robot in MATLAB in both 2D and 3D. The key thing there will be the coordinate transformations. So I will derive, I will show you how do we get these coordinate transformations in a second. Let's first go over the notation. So the GBA represents the coordinate transformation that takes coordinates of the frame A, these ones, XA, YA, and returns the corresponding coordinates, the coordinates of the same point with respect to frame B. Okay, so PA means this XA, so let me do it like this. PA is the XA, YA vector. That's the input, and PB is XB, YB vector. So PA is the vector of coordinates with respect to the first frame, PB with respect to the second frame, and the GPA is a transformation which takes coordinates with respect to frame A and returns coordinates with respect to frame B. All right? Now be careful about the order, because the order really matters a lot, because transformation of coordinates between frame A and B is very different than transformation from B to A. So by convention, so again, we will do the convention that we go from the right. So this means taking coordinates with respect to A and transforming into B as opposed to the other way around. So when you will be doing this, be very careful to think about where am I starting, where I'm going. It's confused again by the fact that you really have to read it from right to left. So this means takes coordinates with respect to A, transformation from A to B gives me coordinates with respect to B. So really I have to be parsing this from right to left, as weird as it might be to you, unless I guess you are trained in Arabic or something which reads from right to left. So to do the coordinate transformations, we need some way to handle translation. So ideally, I would like to represent this using matrices, right? Because we have matrices, we know they are very cool. We know how that composition of transformations, just matrix multiplication. Matrix multiplication is a very elegant thing. MATLAB can deal with it very nicely. So how can I map this onto matrices? Well, I can almost do it except for the translation, right? So I need a way to represent translation using matrices. This way, this trick, if you will, is called homogeneous coordinates. Who heard about homogeneous coordinates before? A handful of you. Typically, I guess in graphics, or yeah, because in graphics, translations we certainly need. So we need homogeneous coordinates. So it's no big deal. It's basically a trick, so we can represent translations also using matrices. So how do we do that? Well, by introducing this homogeneous coordinates by essentially going one dimension up. So I guess the mathematical formalism for this is called the projective plane. So let me explain you the idea, because the idea is very cool. So let's discuss about homogeneous coordinates in 2D. So what do? We essentially create a 3D model for the 2D space. I guess I could be talking about 2D affine space being modeled in 3D linear space. Okay. So let me explain this on this picture. So what I'm interested in is studying points on this plane. Okay. And what I do, I sort of embed this plane into a 3D space. I give it a third dimension, this Z, and I say that all the points I'm studying are on the plane Z equal 1, right? So if I have my 3D coordinate system with coordinates x and y, so the x and y will be also the coordinates in the plane, but my plane where I'm studying my points happens to be the plane Z equal 1, okay? If you want me to write explicitly, I guess I could write it like this, like a set of points of x, y, 1, such that x and y are arbitrary real numbers, right? This is aka Z equal 1 plane, all right? And here's the cool thing. What I will do, I want to study points, so points would be elements of an affine set. I think I'm going to elaborate on this in the next lecture because I think I need to spend a little bit more time discussing it, but I want to finish this so you can start working on your first project. I mean, I'm not so naive that you'll start working on it immediately, but in case you wanted to. So I have a point in this plane, which is a plane with Z1, and I identified with a 3D vector, with a specifically chosen 3D vector, with a 3D vector which essentially traces a ray which passes through the point. Okay, so I will the pretty cool idea of the projective plane is to identify, represent this point by a ray. Okay, in the 3D space. All right. So in general, a ray in 3D space has this equation with some parameters x, y, z, which tell me the direction of the ray, and alpha is a scalar parameter which tells me how far on the ray I'm going. All right. And if I have a ray with coordinates x, y, z, with a 3D vector x, y, z, where does it intersect the plane z equal 1? So now I'm in 3D. I have a ray with direction x, y, z. So if I march over with alpha equals 0, I'm at the origin, right? And as I keep cranking up the alpha, I'm going higher and higher over the ray, right? For some alpha, I intersect the plane. Well, what alpha does it have to be? Well, it must be alpha z equals 1. I'm given the x, y, z, right? So that means that my alpha must be 1 over z, right? If I plug this 1 over z here, I will see that the ray will intersect the plane, and x divided by z, y divided by z, and 1, right? Has to be 1 because that's where the plane is. And here is how the x and z will map to the coordinates on the plane. It's also the same as the perspective camera model, which I will show in a second. Okay. So any direction vector which has the 1 as the last coordinate corresponds to some point in the plane, right? Because any ray will eventually intersect the plane with one exception. That's written here. The exception are the directions x, y, 0, right? What does it mean, x, y, 0? That means the rays are shooting exactly parallel to the plane, right? So that means they will never intersect it, right? The moment you deviate a little bit from the parallel direction, the moment you deviate a little bit, it's intersected somewhere, maybe very far. But if there is 0, we'll never intersect it. So here is how the model of our affine space using this projective plane looks like. If we have coordinates x, y, 1, we basically we say that these vectors represent points in the plane R2. And the rays that don't intersect, that have coordinates x, y, 0, we can say that these will represent points at infinity. Sort of makes sense if you think about it, because if I take a sequence of points and I keep marching on a line in my plane, and if I keep going further and further down, what will be happening to this direction vector, it will be getting more and more parallel to the xy plane, and eventually if I get to infinity, then the direction vector will have exactly 0 there. Do you see this geometric picture somehow? Yep, good. So basically in an affine space, we will say that xy1 represents points, like little dots, and xy0 will be representing vectors in an affine space. But that's not important. It's not that important right now. By the way, this is also how we model projective and also orthogonal cameras, because the same model is useful for modeling the camera, at least the simplest pinhole camera model. If you imagine this is ray of light, so this transformation is essentially the camera projection, right? How the rays project onto the image plane. I will have a slide about this later. Let's do the coordinate transformations now. So the main point of this homogeneous coordinates business was that so we can model translation or using matrices. So we can represent translation in matrix form. All right? So how does it work exactly? Just recall the previous picture before I sidetrack to homogeneous coordinates. We are dealing with this, right? We have two coordinate frames. We have one point. The point has different coordinates with respect to the coordinate frames, okay? In case the coordinate frames only differ by translation, so I have two coordinate frames, just like on the picture before, A and B, and the difference between them is just a translation given by translation vector t, right? In this case, it turns out it's relatively easy to represent the transformation between the coordinates from A to coordinates of B in matrix form, using the homogeneous coordinates trick. So the homogeneous coordinates trick, essentially what it boils down to is appending an extra 1 there. XA and YA, that's the payload, and this 1 is sort of the trick that will enable me to represent translations using matrices. Yep. So this is PE in PA in homogeneous coordinates. This is PB in homogeneous coordinates. And how do I do the translation? How do I represent the translation in homogeneous coordinates using this 3x3 matrix? So this is vector T is the vector which is coordinates Tx and Ty. And this matrix vector multiplication, what it will do? Well, here it's XA plus 0, YA plus Tx1, right? Can everybody do matrix vector multiplication in your mind? I hope so. This would be YA plus Ty, and here the 1, that's just the homogeneous 1 that just gets copied over there. Okay? And it's sort of easy, I guess, to see that this indeed is the correct coordinate transformation, right? Because let's see, if I have some, I might have an example too. Let's see. Yeah, right. So let's say I have a point P here. So this would be my point. So this would be just like one point which I'm observing from two coordinate frames. Okay. So in frame PA, in frame A, the vector representing P would be PA. There would be some XA here and YA here. So PA, let's write it maybe here. PA is XAYA. Let's try to give it some real numbers to get more of an intuition. So if this was unit length vector, this would be like 0.5, 0.5, right? So how do I get the coordinates of the same vector with respect to B? Well, this will be this vector, right? This would be my PB. And turns out that all I need to do is to get the coordinates with respect to B from coordinates with respect to A is to add the translation, the vector T. Okay? So if this T is, I don't know, 2, 1, so in this case, this would be 2.5 and 1.5. Yeah? I'm just giving you some actual numbers to give it a more concrete idea. So all I need to do to change the coordinates is add the vector t. That's exactly what this matrix is doing, and copying the last homogeneous one. So indeed, I have a matrix representation of the translation, and the translation is exactly what I need to do to transform the coordinates. All right? So it's always good to sort of eyeball it to see if it makes sense, right? So if my p had coordinates 1/2 and 1/2 with respect to this frame, it sort of looks like correct that would have coordinates 2.5 and 1.5, right? If you got like minus 1.5, minus 1.5, it will probably be wrong, right? But this probably looks correct. The thing is, if you will be coding, when you will be coding it in MATLAB, when you do it wrong, you will immediately see something is not right. Typically, you translate it the other way around. And remind you again, the convention that GBA means converting coordinates from frame A to frame B. So that's exactly what we did here. We had coordinates from frame A to frame B. How do you think would look the opposite transformation, the GAB, going the other way around? Yes, exactly. It would be 1, 0 minus dx, 1, 0 minus dy, 0, 0, 1. So clearly that's not the same, right? Unless the translation happened to be 0, in which case we are not really changing anything. So that's translation. How do I do rotation? It's pretty much the same story. Here, when doing rotation, I wouldn't even need the homogeneous coordinates because rotation already is a linear transformation, so I don't really need the affine part there, right? The idea is exactly the same. So again, I have some point P somewhere. I have some good example. Like P could be like a point like here. And I measure its coordinates with respect to frame B and with respect to frame A. Guess it probably would be easier if I drew the coordinate frames separately. So this would be my A. This would be the problem here is that there is no translation, so both things are overlapping, which makes the diagrams a little bit confusing. So if this is my A and this is my B, then let's say this was my point. So in the coordinates of A, will look something like this, and those would be the coordinates with respect to A. With respect to B, again, it's the same point. So here is my point P. Here is the vector pointing in it. This would be PA, and the PB would look something like this, right? Basically, if you overlay it, you would get this figure, okay? And I'm drawing this to convince you that if I rotated A to match with B, the difference between PA and PB is just this rotation by angle theta. Okay, maybe that's obvious. Maybe I'm just confusing you by trying to explain it like this, because the difference between the frames A and B is just a rotation by angle theta. So to get the coordinates of the point P from going from frame A to frame B is also just a rotation by angle theta. Okay? And we know from what we started with, we know how to do rotation, right? Here the homogeneous part basically just means appending 0, 0, 1, the last row, and the last column 0, 0, 1 as well. That basically just copies the 1 over and doesn't do anything, really. That's because rotation already is a linear transformation. Okay? In your first project, you also need to do some scaling, I believe. So here is scaling is also a linear transformation. So this would be a simple non-uniform scale. So alpha would be scaling in the x-axis, beta would be scaling in the y-axis. That's how you can do scaling. You can also have shearing. If this 0 becomes something non-zero, then those become shear transformations. And the most important thing here is how do we compose transformations. There is like a little methodology which I would like to explain. So getting these individual matrices for like translations and rotations and so on, that's relatively easy. But if you want to do some more complicated structure like a little robot or even a little robotic arm, something like that, then you need to typically compose a sequence of these transformations together. Okay? And here is a sequence of steps, recommended way of doing it essentially, and you'll need to do it in your project and maybe even a little bit in some of the exams. I will show you 2 examples in a second. The idea is to first draw a clear diagram, label all the frames, and the key idea is to break the overall mechanism into individual transformations between neighboring links. Okay, makes sense, right? And if you keep this notation nice and consistent, then you can just combine the transformations together. If they are represented by matrices, then the combination is just matrix multiplication. That's easy. And notice that if you follow this convention that I'm going from A to B and from B to C and from C to D, then it forms this nice pattern that these C's match and these B's match. So that's what you should always see there. I guess that's easy, right? So let's take a look at a few basic examples. Here is a very simple example. Here, so what's going on in here is we want to transform coordinates with respect to frame A to coordinates with respect to frame C. And we have 2 parameters here. One is the rotation of A with respect to theta, A with respect to B, that's rotation by angle theta. And then we have a transformation between B and C, which is just a translation. So it's basically putting together the translation and rotation, putting together the 2 things I talked about before. Okay? So the transformation between A and B is just the rotation, and the transformation between B and C is translation. So I take this matrix representing rotation by angle theta, this matrix representing in homogeneous coordinates translation by vector t, and the complete transformation transforming coordinates of a point with respect to frame A into coordinates with respect to frame C. So again, I have coordinates of a point with respect to frame A. I transform it into coordinates with respect to frame C, and this matrix GCA will be just matrix multiplication of these 2 matrices. Okay, because now you know all the pieces, right? This does the first part of the transformation, this does the second part of the transformation. Composition of affine transformations is a matrix multiplication in the homogeneous coordinates. Done. If you wanted to multiply it out, you can, but it will get complicated for matrices once the chains will start getting larger. Here is one example, which is just a slightly bigger example, but it doesn't really matter how many links is there because the procedure is the same regardless of how many frames you have there. So here is like an example of a backhoe which has 3 rigid bodies. This is 1 rigid body, another rigid body, 3rd rigid body. Typically with rigid bodies we have one frame corresponding to the center of mass of the rigid body. So this A would be the center of mass, like inertial coordinate frame of one body, D would be the other one, and this G would correspond to some rigid base. You can imagine this is some sort of backhoe, this is some sort of tool which is supposed to be doing something interesting. And there are 2 rotational joints. One is here with parameter theta 1, and another one is here with parameter theta 2. And how do you get a transformation mapping from coordinates in frame A into a transformation into coordinates in frame G? Well, following the same procedure as I explained, right? So first you figure out what is GBA, right? Here this would be some constant translation, right? That's so just I get from the inertial coordinate frame to the coordinate frame centered at this joint, this rotational joint of the mechanism, okay? Then from G, CB, it's weird, right? I would read it from left to right, but it really operates from right to left. This is the rotation by angle theta 1, so I guess I could also better write it as GCB parameter theta 1 GBA. So GBA doesn't have any parameter, it's just a constant shift. But GCB does have a parameter, that's sort of the parameter of the mechanism. Imagine this thing can be moving, right? Then I would go ahead and do GDC, which is again just a fixed thing. The same thing is GDE, so if you wanted, you could even skip from C to E. The reason why you probably would want to keep D here is if you will be doing some dynamics calculations, it's good to have the inertial frame of reference because that is convenient for dynamics. I don't think we'll go to dynamics here though. If you do robotics later on, you will go to dynamics. Okay, is that clear? Everybody understands how to compose this thing? It's really just about being organized more than anything else. So how to generalize this to 3D? I think that's fairly obvious. The same, so we talked before about representing the 2D affine space in 3D linear space using homogeneous coordinates. Obviously, you can take this one dimension higher, right, and represent 3D affine space in a 4D space using homogeneous coordinates. So I do x. What does it mean? Is just append an extra 1 to my x, y, z vector. If I append 0, I get these directions, these points at infinity, if you will. The one funny thing that happens if I have rotations in 3D, they are no longer just rotations about a fixed axis, right? Because in the plane, just one axis of rotation, no discussion about what is my axis of rotation. But in 3D, I can orient my axis of rotation in whatever way, right? So rotations in 3D are a little bit different beasts than rotations in 2D. But it turns out that you can always decompose any 3D rotation into these into 3 elementary rotation with respect to all 3 axes. Rotation with respect to x, y, and z. Okay? And if I extend it to homogeneous coordinates, which I certainly can, all that means is that I append this appendage of zeros and ones. That basically the homogeneous coordinate just gets carried over, nothing special there. If I want to do translations in 3D, it's basically direct generalization of the 2D idea, right? I have just like one more dimension through x, y, z. So this gives me a 3D translation, nothing that special. Same thing with scaling, right? So scaling means I have scales in x, y, and z axes. So by now, I think you know everything. So you could go ahead and start coding up the first project. And I think I will need to elaborate more on some of these affine spaces and so on in the next lecture because I sort of glossed over it. I would like to make it a little more concrete. All right. Any questions? Yep.
Are there office hours?
Yes, the office hours are posted online on the website.
On Canvas?
Not on Canvas, just on the course website. Just if you Google EAS205, will come up. Okay, thank you.